All right, well, we shall begin. Thank you guys for coming, and despite the rain, you guys made it to class, so I appreciate you being here. It's week 5 Monday, and we posted midterm 1 scores. I think you've seen your scores by now, but maybe not. And so, overall, the median was good. Q1, I was happy with. I do want to say a little bit. I know what it feels like to be down here. Okay, as far as a test score goes, it sucks to you see the distribution of scores and you recognize your own score as being somewhere low, and that's not fun. And so, I always want to say that your value and your worth as a person is not determined by your exam scores. Of course, it feels good to get good scores, and it feels bad to get bad scores. But your value as a person is not determined by your academic achievements or your test scores or anything like that. As far as this class goes, we will have 3 exams. So, my hope is that in a future exam, your scores will be better. But even if that's not the case, I want you to feel like as long as you've learned something, right? As long as you're able to do something today that you weren't able to do a few weeks ago, that's a win. That counts as a win in my book, okay? Even if for whatever reason on the test itself, some question you weren't able to get perfectly right or things like that, it's okay. It's okay. And there's so many things that make us people and give us value, and I would say test scores is not one of those things, right? What are the relationships we have with other people? How are we bringing joy to others? Things like that, okay? As far as the exams go, if you want to review your exam, see what happened, you're welcome to come to office hours or a little bit before or after class on Wednesdays and Fridays, okay? You'd have to come to my office in person to take a look at the exam. So that will be that, okay? All right, let's take a look at today's lecture. And again, I forgot my microphone, so you're just gonna have to listen carefully, and if you need to move a little bit closer to hear me a little bit better, feel free to do so. It's week 5. And now we are going to introduce Markov chains. Markov chains is an important part of kind of the Monte Carlo methods. In fact, you often hear MCMC, which would be Markov chain Monte Carlo, and so we're going to just start by introducing kind of the ideas of Markov chains first, and then we'll develop this into kind of a method for generating samples and things like that. Okay, so let's just back up and just get the big picture and see why we even want to deal with this stuff in the first place, okay? And so in the context of Bayesian statistics, we often want to find the expected value of some kind of function. The examples that we were talking about in class was, what's the probability that someone's going to get, 3 hits in the next 10 at-bats or something like that. And we said, in order to answer this, the expected value of some function where the function depends on a random variable, we'd have to solve some kind of integral. And often, in the baseball example, the random variable was the player's batting average. We're treating The batting average is a random variable. The parameter of the distribution itself is treated as a random variable. And we have to, solving the problem of finding the expected value requires an integral. Sometimes it's hard to do it directly. And so Monte Carlo estimation gives us a way to estimate this value by just generating a random sample. And generating that random sample to get our answer is usually fairly quick and easy to do. And doesn't require too much hard math there. Okay, just kind of keeping track of which function is the PDF, which function is your H, which function is, whatever it is you're dealing with. And we said, for a lot of these things, R has its own built-in variable generators. We've got R norm, R beta, R whatever it is that we're dealing with, and that's great. But in the last week we talked about, how do we generate values if R does not have one of these things, okay? And so we saw inverse CDF method, we saw convolutions, we saw rejection sampling, and these are all kind of different techniques we can use to generate samples from distributions that might not be built in. Inverse CDF is great, but it requires you to figure out the CDF and invert it, which can be hard. And rejection sampling doesn't require us to find the inverse CDF, but it can be inefficient, especially in the case where you have a heavy-tailed distribution. And I alluded to this, and when I said you need to have when you pick your proposal PDF, there needs to be some finite constant m, so that m times the PDF of your proposal distribution will at least be as great as your target distribution, okay? But here's just an example where we don't have that, right? This would be a situation where rejection sampling would not be a great choice, because let's say we wanted to generate values from the t distribution with 3 degrees of freedom. And so let's say we decide to take kind of a folded t distribution approach to solve this, okay? And so the PDF of the folded t distribution would have this PDF. It's twice as tall as the regular t distribution. And we can say, well, for the normal distribution, we use the exponential distribution as our proposal distribution, right? So we have the exponential distribution, we've got the folded t distribution, and we're going to say, hey, the exponential distribution worked for the normal distribution. T distribution looks a lot like the normal distribution. Could it work here? All right, and the answer is, well, not really, but we'll take a look, okay? So here's our proposal distribution, e to the negative x. Here's our target distribution, which is the PDF of the t distribution, but twice as tall because it's folded in half. And both of them have the same support, from 0 to positive infinity. So we're thinking, I hope this works. But what we're going to find is that the value m, right, we need to find some value m so that when we do m times g of x, it's going to be greater than or equal to f of x for all of x, okay? But what happens is that if you look at f of x, right, what's the order that it decays? It's going to decay on the order of x to the 4th power, okay? And if you look at g of x decays at e to the negative x, okay? There's an e to the x in the denominator, okay? And so the t distribution is heavy-tailed. It decays a lot slower than the exponential distribution, and therefore, as you go out, m is going to be approach infinity. Okay, m is going to approach infinity, and so no matter if you pick a finite value m, what's going to happen as x goes to infinity, eventually m times g of x is going to be less than f of x, and that's an issue. Okay, so just to illustrate, you know, in the beginning it looks pretty good, okay? Exponential distribution is this. The t distribution is in red. And we say, oh, all I have to do is multiply the exponential distribution by a little constant, and it's going to be bigger than f of x, okay? So here I say, all right, let's use some constant 1.5. Okay, if I use the constant 1.5 for the exponential distribution. So again, I'm doing rejection sampling, right? I'm doing rejection sampling. So we're going to sample from g of x. Now it's g of x times 1.5. We're going to generate values underneath the blue, and then anything, and we'll accept anything that falls under the red. Okay? And so, you know, this stuff gets rejected. We accept everything that falls under the red. But if we zoom in here, if we zoom into this region right here, what do we see? We see that the exponential distribution, because it decays at e to the negative x, and the t distribution decays at x to the negative 4, there's a region where the exponential distribution, you know, dips below the t distribution. Okay, and that's what we need for rejection sampling to work, is that m times g of x needs to be greater than f of x. So our exponential needs to be greater than the t distribution everywhere, okay? So here we can see that the blue line dips below. So we say, okay, well, what if I crank up m to be something higher? M becomes 2, all right? Okay, and so it says, all right, now we can see the exponential distribution is much taller than the t distribution, okay? But even then, as you zoom in, as you go farther out here and you zoom in, you still run into the same problem where the exponential decays and it dips below the t distribution, okay? And you can keep saying, well, let's just keep using a bigger m, all right? And it solves the problem. It just kind of delays the issue, where so now, you know, before it crossed at m was 1.5, it crossed at around 5.5. With m equal to 2, it crosses, you know, 6.3-ish. Okay, with m equal to 6, okay, now the exponential distribution is way taller in comparison to the t distribution. Okay, and we say, all right, maybe this will solve it. Okay, but even then, if you zoom in, right here, it looks like they're right on top of each other. But if you zoom in, again, you still see the exponential in blue dip down below the t distribution in red. Okay, and this doesn't happen until we're out at 8.5, but it still happens. Okay, and so here I say, well, let's try m equal to 60, and at that point, the exponential distribution is way, way, way taller than the t distribution, and then it doesn't cross. The lines won't cross until x is greater than 12. And I go, oh, you know, it still crosses. It crosses after 12. Okay, but we can say, well, you know, how often does the t distribution produce a value greater than 12? Not very often. So maybe this is okay, right? So we could say, you know, if we pick some big m, like m is 60, then the rejection sampling algorithm is going to be accurate for at least where m times g of x is greater than or equal to f of x. So if that's the case, it's going to be accurate at least until x is less than 12, 12.274, and that's going to be accurate for around 99.5% of your values. Okay, and we go, all right, well, this could work. This could work, but when your m is 60, it's very inefficient because you're only going to accept around 1 in 60 proposed values. Because when m equals 60, we're going to generate everything according to the blue distribution, and we only accept values that fall under the red line, right? So what proportion of values are going to fall under the red line? Only a very small number, right? So if we look at what proportion falls under here, you know, it's less than 2% of values. So we had to generate a whole bunch of values according to the exponential distribution, and we're only accepting values that fall under the red curve, which is, you know, less than 2%, and it's still not accurate if we want values greater than 12. Okay, so rejection sampling, it's great, but it doesn't work very well here, at least not with this combination of a proposal distribution and a target distribution. All right, does that kind of make sense? Great. So, let me give you your first view quiz answer. First view quiz answer today is the letter D. D as in dog. D as in dog. Okay. So what do we do? What do we do? Well, so here's just some code that just kind of tries to validate my point. So here I'm using m equal to 60. F is the t distribution with twice as tall. G is our proposal distribution, the exponential distribution. And I generate 100,000 values. And, I calculate my acceptance ratio, which is F divided by M times G. We're going to accept wherever U is less than R. And how many values do we accept? We accept, 1,600 out of 100,000 proposed values. So, we're accepting only about 1.6% of them. So less than 2%. So this is a problem with inefficiency. Okay, now, if we look at the values, we go, oh yeah, that looks like the t distribution. Okay, we can, to take our 1,600 values that we accepted and turn them into a regular t distribution, I'm going to just flip a coin basically. I'm going to assign randomly some of them to be positive values and negative values, because right now it's folded, and I'm going to unfold it by randomly assigning half of these to be negative. Okay, so I'm going to just sample 1 or -1 from the sign. Okay, so we just, with a probability 50%, half of those values are going to be negative and half will be positive, and we take our accepted values, we multiply it by the sign, and so now we have half of our values to be positive and half of our values to be negative. And we say, hey, does this look like the t distribution? I'd say, yeah, it kind of looks like the t distribution. And we can do the Kolmogorov-Smirnov test. And when we do that, it says, yeah, we have no reason to doubt that it came from a t distribution with 3 degrees of freedom. So we take our random t values, compare it to the t distribution CDF, PT, with the argument degrees of freedom is equal to 3. And when we do that, it passes the KS test. All right? So it does work as far as generating values from the t distribution, but it's very inefficient. We generated 100,000 values, and we only accepted around 1.6% of these values. Right? And another con is that it's not going to produce the correct amount of values of x if x is greater than 12, right? So it's not going to produce enough in the extreme tails, which we could say, well, most of our values aren't going to come out there, so maybe it's not that big of a deal. Okay, and you have a lot of solutions. You have some modifications of the Box-Mueller transform, and you can read about them, but there's solutions that we have for generating values from the t distribution. You can also use a convolution to generate values from the t distribution. You generate a normal value, and then you generate a chi-squared value, and you kind of use a convolution that way to get a value from the t distribution. So there's different approaches, and rejection sampling, as versatile as it is probably not going to be a great approach for the t distribution. All right, so all to say is we can improve things by using a Markov chain, right? So, and there's going to be a lot of other situations where rejection sampling is also going to be inefficient, and we don't have some kind of elegant solution to deal with this, okay? And this problem of inefficiency with rejection sampling just becomes even worse when we're dealing in high dimensions, okay? So, depending on what your multidimensional distribution looks like, basically in higher dimensions, okay, you're going to be rejecting even more values, okay? And so an option is to use Markov chain Monte Carlo, okay? And with Markov chain Monte Carlo, we can often produce the values from some target distribution, okay? A key difference here is the values you generate with Markov chain Monte Carlo is that your values are going to be correlated, okay? And ideally, they approach some desired target distribution. So before we can really even get into Markov chain Monte Carlo, we have to even talk about what is a Markov chain to begin with. And so as far as our class goes, we'll just start by talking about discrete time Markov chains. There are continuous time Markov chains, but we're not gonna delve into those, okay? Just we'll keep it simple, and we'll say discrete time Markov chains, which just mean like at this time there's a random state, at this time there's a random state, this time there's a random state, okay? And so we say a discrete time Markov chain of x sub t, so these are random variables, xt at time t equals 1, time t equals 2, 3, so on and so forth. We say this is a stochastic process, okay? And sometimes you hear this word stochastic process. Stochastic just means randomness is involved, okay? And a stochastic process is basically a sequence of random variables, right? So there's some process that generates a sequence of random variables. How can we describe that, okay? And so a stochastic process could be as simple as rolling a die a whole bunch of times. Okay, you're getting a sequence of outcomes to rolling a die, and the process there is basically each roll is independent of each other. Each roll has the probability of 1/6 of generating the values 1, 2, 3, 4, 5, or 6. Okay, and that counts as a stochastic process. Now, a lot of other stochastic processes are more complicated, and Markov chains is one kind of class of stochastic processes, and in particular, the Markov chains exhibit the Markov property, which is to say that the probability that at the next time, at time n plus 1, the probability that at time n plus 1, the state takes on the value j, given everything that has happened before, is equivalent to the probability that x at time n plus 1 equals j, given just the prior value, x at time n is equal to I. Okay, all to say, right? So your life is not a Markov chain because who you are today depends not on just the events that happened yesterday, but also on the events that happened the days before and years before and in your childhood, right? And what happened in your childhood, good things and bad things, have shaped you and molded you to who you are today, okay? And so basically, this is saying the time, what you are today and what you will be tomorrow depends on basically, if we think of each of these time states as a day, it depends on today, the day before, all the way up until we go back in time to your very first day. Now, maybe your very first day you don't remember, but you know, a lot of those things, okay? Depend, right? Whereas this says what happens tomorrow depends only on today, all right? What happens at x time equals n plus 1 depends only on this, okay? I think. And so we say the state space of a Markov chain is the collection of all possible values, right? What could possibly be for each of these random variables? What values can these be, right? And so this is illustrating, you know, x at time 0, x at time 1, x at time 2, so on and so forth until x at time n and x at time n plus 1. That's what this diagram is supposed to illustrate. Okay, and so this is the Markov property. The Markov property means that the probability that the chain or whatever our stochastic process, the thing that generates random variables, moves to state j, that is, produces a random variable with the value j on the next state, depends only on the current state and not previous values, not where the chain has been previously. Okay, and as far as this class goes, we will only consider Markov chains with countable or finite state spaces. That is a discrete state, discrete time Markov chain. And we got all of these terms because you have continuous time and all of these different kind of things, right? And so basically, this just says we have some state space where at least we can enumerate them, at least if they're countable. Maybe there's infinitely many of them, but we're saying we can at least enumerate them, like the natural numbers or even rational numbers. We can kind of like enumerate them. Versus like a continuous thing where you can't list off all the continuous numbers between 0 and 1 or something, okay? Or you have a finite thing and you can just number them 0 through n. Sorry, there's a lot of definitions and technical stuff here, okay? And so we define this thing. We got a transition probability for a Markov chain, and we will say x at time t, okay, where again is defined as this transition probability of this conditional probability, and you say Pij. Pij is the probability that if you are at state I, what is the probability you will transition to state j at the next time frame? So if you currently, if the weather today is rainy, what is the probability it will remain rainy tomorrow? Or what is the probability it will transition to be sunny weather tomorrow? Okay? That would be Pij. You would have P rainy to rainy, or P rainy to sunny. You also have P sunny to rainy, P sunny to sunny. Assuming there's, that would be if there's only two possible states for rainy and sunny. Okay, and if you lived in another part of the country, you could say like rainy to snow, rainy to sun, snow to snow, snow to rain, snow to sun, whatever. There's all sorts of different possible states that the weather could be, and you'd have all sorts of different transition probabilities. And we're basically saying the probability that it's going to be, and I think we would agree that the probability that it's going to be rainy the next day is different than if it was rainy today versus if it was sunny today, right? If it's currently sunny, you'd expect the next day to be sunny rather than rainy, okay? And if it's currently raining, you'd probably expect the next day to be raining more than sunny, or I don't know. Okay? So anyway, we would look at this and we would say, okay, we'd figure out all the possible states I and j in the state space, and we'd have to figure out all of the different transition probabilities. And all of these transition probabilities would then get stored in our transition probability matrix. And so if you have states, however many states you have, you would have probability of going from state 0 and remaining at state 0, the probability of starting at state 0 and transitioning to state 1, probability of starting at state 0 and transitioning to state 2. And you have probability of starting at state 1 and going to state 0, starting at state 1 and going to state 1, state 1 and going to state 2, so on and so forth, going from probability I to state I to state j. And because these are all probabilities, every single probability has to be non-zero, or it has to be greater than 0, I should say. All of them have to be non-negative. What did I say? Greater than or equal to 0. Okay, they have to be non-negative. They can be 0, but they cannot be negative. Okay, and the sum of each row has to equal 1. Okay, not the columns, but the sum of each row. That is because each row represents where you currently are. you're currently at state 0, or currently at state 1, or currently at state 2 is represented by which row you are in. And therefore, if you are currently in one state, you have to transition to somewhere. Either you stay at your current state or you transition to another state, and it has to entail all possibilities so that all the probabilities within one row have to add up to 1. Okay, and so this is expressed as for all possible next states j, right? I being the current state, j being the next state. If you add up all of the states from j into infinity, or however many you have, all of those will add up to 1. All right, is all of this notation feeling okay? Okay, good. Second view quiz answer today is the letter C. C as in cat. C as in cat. All right, so this is a very simple diagram. We're going to have a Markov chain with just 2 possible states. Okay? And the weather worked out just perfectly for this example, I guess. So we have 2 possible states. We're going to just say A represents sunny weather, B represents anything that's not sunny, which will be cloudy and rainy or whatever, okay? And so today we are currently in state B today. All right. And so we have different possible transitions. If you are currently at state A, you could remain at state A. If you're sunny today, it could be sunny tomorrow. If you're at sunny today, it could be raining or cloudy or whatever, something not sunny tomorrow. And if it's not sunny today, it could remain not sunny tomorrow. And if it's not sunny today, we could also transition to a sunny day. So here are just some completely made up numbers. And we could express them with this transition probability matrix like this. Okay? Our transition matrix looks like this. Each row adds up to 1. And this 0.7 represents the probability of transitioning back to A if we are currently at A. So if we're in row A, what's the probability I end up back in A? That's 0.7. So if it's sunny today, the probability it will be sunny tomorrow is 70%, which means there's a 30% chance that it's not going to be sunny tomorrow. Right? And then as far as B, if it's not sunny today, there's a 40% chance that we transition to sunny. And there's a 60% chance that it remains not sunny. Okay? Each row adds up to 1, which is to say the probabilities of all arrows originating from some node or some state must add up to 1. Okay? All right, is this good? Our little diagram here, all right, and so obviously this gets more complicated as things go. So here's an example. This is the Ehrenfest-Ern model, okay? And we can use this as a mathematical model for the diffusion of molecules, all right? And so you have these 2 urns, one labeled A and one labeled B, that contain a total of n balls, which each represent a molecule. And what we're going to say is that at each step, a ball is randomly chosen from all n balls and moved to the other urn. Okay, that is, we either go into, if the ball exists over here, we move it over here. And if the ball exists over here, we move it over here. So x sub n will denote the number of balls that exist in urn A, right? Which means you have n minus x sub n in urn B, okay? And therefore, the state space for x sub n is anywhere from 0 to n, right? We have a total of n balls. We can have, how many balls are in urn A? It can be any whole number from 0 to n, okay? And so the sequence is going to be the values x0, x1, x2, all the way through x at time n, okay? With a state space where the values could be 0, 1, 2, all the way up to however many n balls you have. Okay, so let's say at some step n, we have I balls in urn A, okay? That is to say x sub n, the x variable, random variable x at time n is equal to I. right? So if currently x at time n is equal to I, then at the next step, what happens? Either we take a ball out of urn A and it goes into urn B, and so the number of balls in urn A drops down to I minus 1, so x at time n plus 1 goes down to I minus 1. Or we take a ball from urn B and put it into urn A, and therefore the number of balls has to go up to I plus 1, okay? It's not, according to this Ehrenfest urn model, we cannot start at state I and remain at state I, okay? Because either a ball has to move over or a ball has to move somewhere, right? So if the ball is chosen from urn A, then we go down from I to I minus 1. If the ball is chosen from urn B and goes into A, we go from I to I plus 1. So the ball is chosen randomly among all n balls. Each one has the same probability, and so the probability that a ball is chosen from a particular urn is going to be proportional to the balls that are in the urn. All right, so here's a diagram. Okay, so let's say let's say we have a total of 4 balls. Okay, we have 2 in urn A right now and 2 in urn B. So this is just one possible state. Okay, one possible state is that x at time n is 2, and then we ask, okay, where can we end up? Okay, well, we could pick the first one from A and move it to B, and then we will go from 1 to 3. All right, or we could pick this one and it goes from currently at 2 down to 1, currently at 2 down to 1, okay? Or we could pick this one and it goes, currently we have 2 balls in urn A and we end up with 3 balls, or we could pick this one and we currently have 2 balls and we go to 3, okay? So the probability of going from 2 to 1, there's a total, out of the 4 possibilities, okay, 2 of them correspond to going from state 2 to state 1, so that happens with probability 0.5, and 2 out of the 4 correspond to state 2 to state 3, which also corresponds to a probability of 0.5. So our transition probabilities, that is, the probability of going from 2 to 1 is 0.5, and the probability of going from 2 to 3 is 0.5. And then the probability of going from 2 to 2 would be 0, probability of going to 2 to 0 is 0, probability of going from 2 to 4 would be 0. All right, so this is what we have. Okay. What are our transition probabilities if we have 3 balls in urn A? Okay, with 3 balls in urn A, okay, we have a total of 4 balls. We have 3 in A and 1 in B. So what could happen? We move this one over, we go from 3 to 2. We move this one over, we go from 3 to 2. Or we move this one over and we go from 3 to 2. Okay, another possibility is we move this one over and we go from 3 to 4. So what's the probabilities of going from state 3 to state 2? That's going to happen with probability 3/4. If we currently have 3 in A, what's the probability we end up with 2 in the next state? That's going to happen with probability 0.75. If we have 3 in A, what's the probability we end up with 4 in the next state? That's going to happen with probability 1/4, 0.25. Does that make sense as far as these transition probabilities? Okay. And so you could go through and you could think about, okay, what are the transition probabilities for every single, what are all the transition probabilities? And we get this. This is what we get, okay? If you currently have 0 balls in state A, or in urn A, then 100% at the next state, you're going to have 1 ball, okay? All right, so the transition probability for that row is going from 0 to 1 has probability 1, okay? And it's not possible for anything else. Everything else will have these probabilities. Going from 1 to 0 has probability 1/4, 1 to 2 has probability 3/4, 2 to 1 has 1/2, 2 to 3 has 1/2, 3 to 2 has 3/4, 3 to 4 has probability 1/4, and going from 4 to 3 has probability 1. Okay, so each row equals 1. And so this would be our full transition probability matrix for an Ehrenfest urn model with 4 balls. Okay, and this is what the Markov chain diagram would look like. If you're currently at state 0, you would have to go to state 1. If you're currently at state 1, you can go to state 2 with probability 3/4, or you could go back to state 1 with probability, or state 0 with probability 1/4. If you're currently at state 2, you can transition to state 3 with 1/2, or transition to state 1 with probability 1/2, and so on and so forth. And this is what the model looks like. Okay, and if you wanted to generalize this for any integer value of n balls, okay, you could go through and verify this, but then the transition probability of going from I to I minus 1 will be I over n, and the transition probability of going from I to I plus 1 will be 1 minus I over n, and then and you have 0 probability for anything where you're gonna if you're not going to I minus 1 or I plus 1. And so therefore you can kind of list off all of your transition probabilities kind of with just this simple formula here. Okay, and I'll leave it up to you to verify that on your own. Okay, let's take a look at another stochastic process that can be represented as a Markov chain. Okay, so we could just say a random walk. A random walk would be a discrete time stochastic process, and we say, hey, this is the path of like a particle that moves through space, right? So this was I forgot. Einstein won the Nobel Prize for Brownian motion, right? Do you guys remember this? No. Okay. So basically, Einstein said if you put like a small little particle in water or air, basically it bounces around, and the path it follows is basically a random walk, because you have molecules in the air hitting it kind of from a random direction and all sorts of stuff here. Okay. Oh, this is what I wrote here. All right. So the path the particle takes as it moves through a liquid or gas in continuous time would be called Brownian motion. But we can also say, hey, this also works as far as the path an insect might take as it searches for food, or a gambler's wins or losses. Okay, stock prices, maybe we treat them as random walks, maybe with a slight bias towards being positive or negative in a bull or bear market or something like that. But basically, we're just going to look at some one-dimensional random walk. Okay, either you go up or you go down. Okay, and so here we're just going to say, okay, what value do we have? And we'll just define this on the integers to just keep it simple, right? So there's all sorts of stochastic processes. We can say you either move up a whole an integer value, like which is what we're going to say today, but you can also say, oh, we only move up or down, like sometimes big values and sometimes small values and things like that. Okay, so we're just going to say the walk starts at 0, and at each step we move to the right 1 unit with probability p, and we'll move to the left 1 unit with probability q, 1 minus p. Okay, and so we'll say, hey, at x at time 1, if we start at 0, x at time 1 is going to be 1 or negative 1, 1 with probability p, negative 1 with probability q. Okay, and if you're currently at state I at time n, okay, then you will end up at I plus 1 with probability p and I minus 1 with probability q. And this would be a Markov chain. And here it's technically infinite. Okay, we don't have a finite matrix because we can't list off every single possible integer value, and it is theoretically possible that your I ends up at, a billion or something, or it ends up at negative a billion. Okay, I think we'd be surprised. But certainly that's possible. I mean, well, I guess it depends on what your P and your Q are, right? And so you could keep going higher and lower and things like that. And so we can't create a finite matrix, but we can still describe what our transition probabilities are, right? So if we're currently at state I, the probability that we'll be at j, okay, we have p if j is I plus 1, we have q if j is I minus 1, and we have 0 otherwise. So what does this look like? Okay, we can say, oh, you know what? This random walk, we can express it as just the sum of some IID random variables, right? We can say the values y, take probability, take on the value 1 with probability p, and take on the value -1 with probability q. And we can say, okay, well, then the Markov chain is going to just be the sum. We'll just take, we add on whatever y at time n is, okay? So this is what it would look like in code. Here I just said, hey, let p equal to be 0.5. Let's do 1,000 states of this. And I'm going to just generate some IID values for y. Y is either going to be 1 or -1 with probability p and q. We do this with replacement. And then x is just going to be the cumulative sum of everything where we started off at 0 and we just keep adding y, being 1 or -1. Right? So here's one outcome. We go down, up, and sometimes we go down a bunch of times, and this would be a random walk. Right? Here's another random walk, okay? And so we can see, sometimes we end up negative. After 1,000 iterations, we ended up down at -40. After 1,000 iterations, we went up as high as +50 and things like that. And this was just with equal probability. P is 0.5 and Q is 0.5. But we could have picked any other numbers if we wanted to as well. And the way our random walk would look would be different. So these are both examples of Markov chains. This one was finite, and we could create the transition matrix. This one is not finite. You can't draw out the physical matrix, but you can still describe exactly what these transition probabilities are. And certainly we can make any of these stochastic processes more complicated by including additional random variables, such as, what's the size of the step. Here, the sizes of the step are either 1 or -1, and we kept it very simple. But again, you can make things more complicated by including the size of the step as part of your random variable, and then certainly your transition matrix gets, or your transition probabilities get a lot more complicated. But we're just looking at discrete time, discrete state probabilities right now, or Markov chains right now. Let me give you your last view quiz answer. Today's last view quiz answer is the letter A as in apple. A as in apple, okay? And we will continue to develop Markov chains as an idea so that we can use them to generate values from a random distribution, okay? From a probability distribution, a desired probability distribution. Right now, they are just generating random values and random variables as part of some kind of stochastic process, but we'll generate we'll talk about the Markov chain as a means to generate values from a probability distribution. Okay, that's it for today. We'll end here. We'll see you guys on Wednesday, and have a good day.